Well, let's do the thing. I can't help it. I'm still fiddling with this deck. I've done this versions of this talk now since 2019 because I was thinking, hey, it's coming into the 2020s. I should be sort of looking forward. Like this would be a fun talk to do. And the podcasts help all of that. You know, the upside to making any .NET Rocks listeners, a few in the room, excellent. So you know, I interview every week. I get a chance to talk to a lot of luminaries, and you know, you sort of get a sense of the gestalt of what people are working on. Admittedly, with a Microsoft bias, you know, to be honest. .NET Rocks is for .NET developers. Now, not everything that .NET developers do has to be Microsoft-based, but a lot of it is. Run as Radio is more on the IT side. It definitely got a Microsoft bias as well. But when you try to look forward out 10 years, that's pretty hard. You know, Niels Bohr is the originator of this quote. The prediction is difficult, especially about the future. I don't know what else you'd predict, but yeah, it's going to be difficult. But when we're talking about software, we have to talk about the hardware, the platforms that it run on. That really is what dictates us. Logically, software trails hardware. So when I want to predict the future, and I'm very much a believer in William Gibson's statement, the future is here, it's just not evenly distributed. So you can go into spots out in the world where they are pressing against the edge of things. Like how will that expand? How will that cover more things? You know, the cloud's not a big innovation now. We're pretty comfortable with it being around. And if you're going to stick around tonight, I'm going to tell an early cloud story as part of the evening's festivities. But the cloud's insanely important. This is a new utility. We only have a few utilities in civilization, right? Clean water, sewage systems, electricity, internet connectivity, telephone. You know, those are utilities. And now because of the internet, we also have the opportunity to have compute on demand. You know, you open the tap and bits come out. And it's that combination of cloud and the smartphone that has really shaped society for the past decade or so. That has changed a lot of things. Mostly, we've generated a tremendous amount of data about ourselves, that lots of people are exploiting. And I think we're at a turning point on all of that as well, but that's not necessarily a software problem per se. And none of this is any prediction. These are logical trends. More compute, more devices, more data. That's pretty predictable. But if you're actually going to think about what's going to change in the next decade, what's going to be different in that time, well, then there's a few more interesting things. One of them is Moore's law is going to end. Now, Gordon Moore is one of the principals at Intel back in the day. When Intel spun off from Fairchild Semiconductor, their first business was making semiconductor RAM. Now, this is in the 1960s when a lot of storage was actually done with ferrous cores wound with copper wire. So a semiconductor storage thing was a big deal. The CPU comes later. Not until 1970 they built the 4004. And so this observation that Gordon Moore made was really about RAM. It was that, hey, for the same amount of money, we can double the number of transistors on a given piece of silicon every 18 to 24 months. That's essentially what he said. It's hardly a law, because you know, laws are things that happen whether you want them to or not. Gravity's a law. You really don't have a choice on that one. Right? The reality of that statement was, if a large group of people work extremely hard, we can double the number of transistors roughly for the same production cost. And that trend has continued up until now. So if I pull the data set of CPU performance from Wikipedia, I get a graph like this. Literally from 1970, from the original 4004 up to current generation processors, with a geometric scale on the left side, we get a pretty good line. Now, if I only went up incrementally, this graph looks more like the hockey stick because the numbers jump so radically as they keep on doubling. And it's hard to get your head around billions of transistors and the fact that we've continued this trend for so long. The fun way I like to describe it is to show you one of these. What's this? Warp drive from the Enterprise? Nope, that's this. This is a Cray 2 supercomputer. And in 1985, this was the computer of choice. If you had $16 million burning a hole in your pocket and about 200 kilowatts of power, you could have one of these supercomputers. There was only a few hundred ever made. They were typically products for governments and universities, and they modeled nuclear explosions on them. They helped calculate some of the satellite trajectories for the great exploration satellites. And it had about 1.9 gigaflops of processing power, 1.9 billion floating point operations per second, 1985. Fast forward a few years to 2011, the iPad 2, about $800. Battery operated, also has 1.9 gigaflops of processing power. And you play Candy Crush on it. You give it to children. and let's face it, that's 2011. That's not fast. You know, what's fast today? Well, arguably the fastest piece of consumer computer equipment would be the NVIDIA RTX 4090, okay? If you can find one, and they're coming in around like $2,000, like that's a lot of money. 450 watts of power, so hope you got the big power supply, and a lot of extra fans. 82 teraflops. So 40,000 times faster than that iPad 2. That's a lot of Candy Crush. And of course, that's just a consumer product, right? In theory, we can buy this at the local store. When you talk about the most powerful computers in the world, there's been a race going on for some time between the Japanese, the Chinese, and the Americans to build supercomputers. The current leader at the moment is Japan's Fugaku supercomputer. There's about 7.3 million cores, 29 megawatts of electricity. So bring your own nuclear reactor. 200, and it comes in at about 415 petaflops flat out. So 220 million times faster than the iPad 2. Moore's law, right? That as we can keep harnessing more and more compute. Oh, by the way, about $1 billion. So if you're trying to pick between the supercomputer or the B-2 bomber, you can get one of these. There are, of course, exactly only one of these, and that's as many as we need, right? There's only so many problems this computer can actually do that's meaningful. It models airflow simulations across airfoils. It's the reason that hurricane and typhoon prediction is so accurate these days. These kinds of machines do that work. Very complex modeling. It's not a normal set of problems. They're a narrow space to operate in. But we were talking about Moore's law, right? That this is going to end, that we can't just keep going this way. Now, why? Why would this end? It's been fun. Right? Our careers, 50, 60 years of just, you're always going to get more compute. We don't have to make our software all that efficient. We're going to get more compute. We're running out of silicon, not actually physically, but literally the space. So the current sort of state-of-the-art process is somewhere around 5 nanometers. Right? And again, a nanometer is an impossible thing. It's a billionth of a meter. Like, how do you express a billionth of a meter to someone? One of the ways I do it is say, okay, imagine I want you to wait for a second. That's pretty easy. What if I asked you to wait for 1,000,000 seconds? How long are you waiting for? 1,000,000 seconds. It's like 11 and a half days. So, get a coffee. What if I asked you to wait for 1,000,000,000 seconds? Well, that's 33 years. So a second is to a nanometer as 33 years is to a meter. Right? That's the crazy thing. These are really, really small numbers. It is hard to conceive of a nanosecond. It is hard to conceive of a nanometer. But the question you have to ask yourself, like this is the IBM 5 nanometer process. So each one of those cells is about 5 nanometers across. Here's an electron tunneling microscope image of a silicon substrate. So the yellow bumps you're looking at, silicon atoms. The blue gaps are the boron in the substrate that makes it a semiconductor. When you're down to 5 nanometers, a silicon atom is 111 picometers across, or about 0.1 nanometers. So you're talking in the neighborhood of 40 atoms across for a transistor. It's just not a lot of atoms. So we're kind of getting to a point where you're running out of enough atoms to actually act as a semiconductor. It cannot continue. Now, there's some cool experiments going on with single atom transistors and so forth. But remember the other part of Moore's law, which was with some effort for the same amount of money, we can double the number of transistors on a piece of substrate, right? And so most of the techniques we're looking at beyond this get really complicated. It's not that you have to make a transistor, it's that you need to make tens of billions of them for about $1,000, retail with profit margin. So we've had an extraordinary run of this iteration, and it cannot continue. And that's okay, because it's its own problem too. Because we've always had more compute coming, we kind of not fix some things. You know, the Intel boys still have the same set of instructions in their CPU that they put in 1984. And every time they tried to make a new processor that didn't follow that instruction set, we wouldn't buy it, because carrying software forward is important. And so the big thing you're going to see as the Moore's law stops iterating is that we'll start changing architecture. So that Intel architecture, which has just been built on and built on and built on since the 1980s, and so it's really quite complicated, is already being superseded by simple architectures like ARM. ARM was designed much later and with a broader thinking about what modern processors look like that was more inherently parallel. That mindset lends itself to a lot of efficiency. You move electrons a lot less distance in an ARM processor than you do in an Intel processor just because of that compatibility baggage. And I think we're going to see more of that. And you've seen it already. If you've looked at an M1 processor and now the M2, what Apple's done there by unifying modern processor design with modern GPU design with some interesting other calculation engines and RAM all in a single package is arguably the best compute device we have right now. I am stunned at how good an iPad Pro is with the M1. It's an extraordinary machine. And we're kind of getting to sufficiency, which is not in our nature as computer people. Remember we used to care how many gigahertz were in our machines? They used to market on that. It used to be, because all the machines were beige. It's like, look, they're all equally ugly, but this has more gigahertz, right? That's how they sold it. Today, actually, the machine is beautiful. And you couldn't care less how many gigahertz in it. It doesn't really matter. And besides, you're not out of processing power, you're out of bandwidth. Speaking of bandwidth, everybody really excited about 5G? Oh boy, well somebody was at one point, we were lots of talk about it, we're using it today. I mean, in the end, when it comes to wireless, and this is another primary constraint that we have, if you want to move more data in a given amount of time, you have to go higher frequency, right? So we were happy living in our 4G land at a frequency, typically there's variations country to country and different rules of around 2 gigahertz, the microwave frequency range. 5G goes up as high as 20 gigahertz. So it can pack a lot more data without a doubt. The problem is as the frequency goes up, the penetration ability goes down. If you're old enough to remember like 2G and 3G, I mean, you could be sitting in a concrete bunker and still get a call. Not so much with 4G, you kind of need a pretty clear shot. Wooden walls is fine. Anything with stone or concrete, you probably didn't get signal. 5G has problems with things like leaves, people. We did a demonstration where we were literally in visual view of a 5G tower holding the phone looking at we had a signal monitor on, and I just turned around. And apparently, I'm a signal blocker. So 5G is great in the sense that it has the potential to move a lot more data, but it's much more sensitive to the bandwidth. The architecture also allows for much smaller cells because we have far more devices. Like they're doing some useful things. There's a 6G in the works, but we're continuing to struggle with the wireless. This is the challenge of what do we do to maintain connectivity for more and more and more devices. And I know I'm in Australia, so of course you guys all love Starlink because you're a big country with a lot of open space and not a lot of cables running all the spots. I mean, if you're in the city, it's fine. Gigabit fiber is always going to be better. I have a place in the city that can't get gigabit fiber, but so hey, yay for cable modems. But we also have a place up by the ocean where we don't get anything. And we use Starlink. Starlink's good enough. It's decent and doesn't depend on a lot of other things. They're continuing to expand it. In theory, it'll get faster. Now he's dealing with the problem that more and more people are using it, and it's actually consuming the bandwidth limits of its satellites. Interesting problem. And I bring those pieces together, this more and more compute in smaller and smaller packages, and better communications, because we are talking in this idea of ubiquitous computing, that once upon a time, these machines were large and discrete and expensive. They had names. We cared about them. And now we're finding compute in everything. It's easier for general purpose computing to be a standardized device that's easy to program by any of us. So we're naturally going to be surrounded by more and more computing devices. We're seeing it happen now. Your appliances are getting smarter. I mean, I don't say they're doing it well, because it turns out software is hard, but they have the compute power. And that opens the door for a lot of possibilities. And that is an interesting change over the next few years, is that we're just going to have to deal with, we have many more compute devices around us, and our contexts are going to matter. Our ability to move our identity into a device, do some work with it based on access to our information, and then leave that device. We're still not good at that part, but we're going to need to be. It's a ton of work. Now, I'd be remiss if I didn't talk a little bit about the pandemic, just because it's been exciting for the past couple of years. Last time I was here in this room was 2019. And glad to be back, but I don't know what you did for the past 2-3 years, but I hung around home quite a bit. Our friend Satya Nadella said that in the early parts of 2020, 2 years of cloud migration happened in 2 months, as everybody had to suddenly work from home. A whole lot of action went on. I'm looking forward to the historical analysis of those early months of 2020, and I'm kind of staggered that the internet survived. Remember when the EU asked Netflix to turn off 4K mode? Like, I think that's how close we were. That we were just running out. Everybody needed a lot of bandwidth all at once, and we were running low. And same with the cloud hardware. You've seen already some constraints where the big providers have left old machines continue to run while they're adding new machines as quickly as they can, and capacities are kind of at the limit. So we accelerated a bunch of things. Now, I'm probably amongst some group of people that were not as affected by the pandemic in a lot of ways. We were working from home before it was cool, right? It was already a normal part of our job. And we watched everybody else learn how to talk on video cameras. We didn't have a big problem with it. And that part's starting to subside. You know, we're getting past these elements, and I think we're all a little sick. What I find fascinating is I think virtually every person involved in technology in the past 2 years actually hit a limit on how much screen time they could stand. I didn't think I had a limit, but I found one like a year and a half ago. I'm like, you know what I really don't need to do? Look at any more screens. The bigger impact was the efforts to defeat this illness and sort of keep our society together has spent a tremendous amount of money. It's disrupted supply chains, and we are having economic challenges. And so we're seeing the shape of the downturn now. There's a bunch of reasons we could talk about it, whether we're dealing with it well or dealing with it poorly, but we can't ignore the truth. And again, the good news is we're in computing. We're a pretty efficient industry all in all, and we can benefit and be helpful through these kinds of crises. But we haven't had one in a long time. There's a lot of folks who have had a career in computing that was only growth, that things just kept getting bigger and bigger and bigger. Now, I started writing code to pay my rent in the early 80s during recession times. And that was a time when we talked a lot about return on investment. That the way we talked about writing software was how it would increase the efficiency of the business. Right? This was a time when there was problems with finding workers. And so the fact that we could automate some tasks so that one person could do more was considered a huge feature. And so it's how I sold a lot of software. And I bring it up for all of you just to say, if you haven't thought about this, it's probably a good time to do so. The question that I ask first and foremost is, do you know how your company makes money? Because rarely in our role are we responsible for that. Typically, we are building tools that allow others in the company to generate money. So it's useful for you to be aware of how that works and make sure you're contributing to that. Because there's plenty of development projects out there that don't tie directly to income for a company. And those are typically the projects that get cut when things get tight. So if you focus on projects you know help your company be successful, you're going to stay busy and help the company just at the right time, the right way. So it's worth considering. Again, it hasn't been a big issue for a long time, but it sure is right now. And it may get bigger before we get through this particular incident. All right. fewer broad strokes. Let's talk about known technology, stuff we care about. I don't see browsers going anywhere. The browser is kind of the de facto client these days, right? One would even call them the smart clients. I live enough time in the IT side of things to say, why do I like browsers? Because it's a security context I understand and trust. It's already on all the devices. I don't have to install a thing on the device. All of that internal software that my company needs can come through those browsers' context. That's sufficient. It's safe. It gets rid of a lot of those install problems. And so, you know, that dominance is going to stick around for a long time. How you build software for your browser, that's only continuing to broaden. I grabbed a set of icons off the internet, you know, so probably recognize some of these frameworks. If we wait a minute, there'll be another one. And it's interesting to think about, you know, how mature these are, how stable these are, how well supported they are, that you can bet on software that your company is very likely to run for a long time. Not that it, just because there's a new version of Angular coming means that the old version of Angular stops working. I still know there's some 1.1 people out there that are happy. They don't care that we're on, what is it, 14? Close enough. I also think that the progressive web app is an excellent addition to that because it allows regular users to forget they're using a browser at all. We gave them an icon, that's the important part. We gave them ubiquitous connectivity because disconnected clients aren't any fun. But we can fake pretty app-like behaviors with some of the PWA features. And we've got Mr. Sanderson around here somewhere. He hates it when I show his face on the screen, but of course he's the one in the Microsoft world that did an implementation of C# in WebAssembly and brought us Blazor. And there are some serious Blazor fans out there, mostly folks that have been doing web development for a while in the Microsoft community and find this very approachable. But let's face it, what WebAssembly's really brought us is an equal footing for other languages to work against the browser context. And that just opens the door to browsers continue to dominate further. It doesn't mean there isn't an effort for other clients, and I'll talk about that in a bit, but you can't argue with, if you're writing code for companies, in an awful lot of circumstances, that's an easy way to go. I got to talk about Web 3, even if I only make fun of it. Of course, they're playing off the Web 2, which was sort of the web that appeared post the dot-com bust in 2000, 2001. That was kind of Web 1. I look at Web 1 was when your web server was under your desk. Web 2 was when your web server was Facebook, right? And now Web 3 really speaks to this idea of getting to decentralized again. Now, it doesn't mean I want to go back to the server underneath my desk. It means that I don't want everything behind a walled garden. I want a little more control and context. Probably means I'm running in the cloud. I hear lots of pro-Web3 people talking about decentralized networking while also saying, and you have to use my server, which seems like a conflict of interest. So I'm pretty skeptical of what's going on, but I'm kind of breaking out the pieces and saying, okay, decentralization seems like a good idea. And it's something we can do. It has distinct benefits. We just have to figure out right ways to go about it. I don't have a whole lot of problem with blockchain. I think blockchain's biggest problem is it's associated with crypto, and crypto I got problems with. But I see blockchain in the same relationship with crypto as I saw BitTorrent's relationship with Napster, right? Napster was actually a criminal enterprise that depended on BitTorrent to distribute music, and blockchain's pretty much in the same boat. An awful lot of crypto is pretty scummy business, but it happens to use blockchain to operate it. I've also seen some great implementations of blockchain for very useful things. And so I don't think that technology is going away. I don't think it's a panacea, but then none of them are, right? For certain applications of distributed information where multiple transactions need to be entered from multiple sources without a central clearinghouse, blockchain. But there is just not that many applications that need that. Most organizations, as soon as they go, we want some blockchain, it's like, are you okay with people putting the transactions in your system that you don't deal with? And like, no, we're not. It's like, okay, don't need blockchain, moving on. And of course, we're living in Microsoft land, so a little bit about .NET. .NET turned 20 years old in February this year. .NET Rocks turned 20 years old in August. So we got there. I didn't show up till a couple years later, so I haven't been doing it quite that long. But Microsoft's now on a steady cadence where they're going to push out a version of .NET every November for the foreseeable future. Certainly for this year, for 7, and next year for 8. Nobody's talking about 9 yet, but that also means that they're slipping features to deliver on time. And you certainly saw this with Maui. Maui was supposed to show up with 6, and then they said, we're not quite ready, here's another community preview. And then in spring this year, they said, here's some more community preview. I think Maui really shipped in August. When they did the Maui Day of .NET is when I think we kind of got to 1.0, which means we're only 2 more versions away from this thing being good. What's Microsoft trying to do here? Well, this is the unification of all of the XAMLs. So there's more XAMLs than you knew inside of Microsoft, right? Windows had literally its own implementation of XAML that they called UWP, and ultimately WinUI. Then there was the WPF edition that lived over in dev. And then there was Xamarin Forms, which now had become part of Microsoft as well. How are you going to put all these things together? And ultimately, you know, Xamarin Forms was sort of the smallest set that you had to build up from, but also was the group with the least amount of political clout inside of Microsoft, so they really struggled with this. But Maui is actually the success story of them being able to get WinUI and WPF and Xamarin Forms, rationalize them all together into a unified XAML stack. That's good news. Are they solving a problem we need solved? Well, yes, in the sense of we're still trying to figure out how to make great multi-client apps. The web is one approach to it that's going to run on your phone and your tablet and your PC, but that has its own limits. So when we start talking about more native applications taking advantage of it, do we have a better client choice? And if you listen to .NET Rocks, you know I've been running the gamut on every library I could find. I even had the Flutter guys on because I think what they're doing is pretty cool. They've done well enough in the client in the mobile space. They're now making a client for Windows, and I thought, well, we better talk about that. And the same with guys like Avalonia. Like there's a ton of them. And then for me, as someone who gets to survey the landscape all the time, when I see a fragmentation like this, lots of different libraries working, I know this is an unsolved problem. We're still struggling to say, what's the right way for us to write code once and run on all the devices? Because that's what our customers want, right? Our customers couldn't care less what device you wrote it for as long as it runs on their device. And generally speaking, our employers are not interested in you actually spending more time and effort to work on more devices, as long as it just works everywhere the CTO sees it. That's the important part. There is another approach coming from Microsoft as well. If you haven't looked at it, you got to take a look at Power Apps. Now, I don't like the way they pitch this product. I think citizen developer is a dumb term. I think it's derogatory, actually. I like domain expert, because that's actually what I need. And I've seen generations of domain experts become developers at different times throughout software development, right? If you go back to the Axis and VB days in the early 90s, these were rapid application tools with minimal coding initially. They eventually got more complex over time, but it was the same sort of thing. You weren't a real programmer, you were programming VB. Real programmers program in C++ and deal with UACs. Right? You crash, the only way you know you're really programming is because Windows keeps crashing. Excellent, right? VB was a way not to crash Windows and still write code. And I was a VB programmer. I switched from MFC to VB in a second, because you know what my customers like? Software that works. And I cried all the way to the bank. And I feel the same. I look at Power Platform and I go, this feels the same thing. That domain experts, people who really understand the business problem, can sit down and build a decent cross-platform client that works against cloud data, right? What the Power Platform has really done is puts table stakes on, works on every device, uses the cloud as a back end. Microsoft's created a fairly restrictive licensing model for this. This is really only for internal apps because they charge per seat. And I don't think I would put that on the public. That looks like a good way to go broke. What I find fascinating and been paying close attention to on the shows is folks building apps this way also drop into your normal CI/CD pipeline. So their source code gets checked in, they get distributed the same way, like it's just more code being written in a different way. And now they're providing libraries for us as developers to assist them. Not only I can put in back-end APIs that it can call, but I can build custom client components that will work for them as well. So we can start tailoring the UX look we want for all the Power Apps inside of our organization by building custom components for them. So it's not like any of us were getting to the bottom of our to-do list, right? There's so many forms over data projects that need to be done. If someone is willing to do them that's not me, I'm willing to let them do it and probably help them out as long as we can give them some guidance that we make testable software, reliable software, software that can be updated routinely and be maintained. And these tools can do that, although they are young so far. If you don't care for Power Platform, you will also notice there's a couple of dozen products like this out there. Again, this is clearly an unsolved problem, but the forms over data across multiple clients and clouds is a necessary problem space that's trying to be solved in a bunch of ways. And so how you write your code matters for that. I talked briefly about containers just because I think containers have not gone as far as they can go. The idea that we run code more and more in a virtualized space just makes sense, right? That we get more abstracted from the hardware, we get more abstracted from the operating system, right? Containers are virtual machines that have kind of got the operating system stripped out of it. So you're a little bit smaller, a little bit leaner. I think we're going to see more of this because we don't trust software, nor should we. We want to be able to put software in as small a can as possible with a very specific manifest that says you are allowed to do X, and if you do anything that's not in this list, I will stop you. And that kind of virtualization is how we get software to work and play well with each other. We're not fully done with this. There's more to be developed here, and it's going to affect how we write software. The biggest thing for me is, when we build software, how clear are we on the manifest side? What do we know that our software needs? What libraries does it depend upon? What ports does it depend upon? What calling stacks does it need? So that we could put that into a document. We could put that into a manifest of some kind so that something could enforce all of those rules. If this feels a little overwhelming, I don't blame you. Change is hard, but there's more than one way to have a career. Often when we first get into software, we're really hooked on the newest bits and you're ready to jump to the next stack and like we're all about the new things. And then at some point that becomes less exciting. It's like, really? I'm going to reinvent forms over data again. Yay. Right? And it might have been fun the first few times, but it gets less fun. Depends on who you are. Some folks just dig this. They always want to try the next bits. But also you start building up a repertoire of work. You've built a bunch of stuff for people who want you to keep taking care of it. And that's okay. There's more than one way to have a career. It's pretty normal, actually, to hit a point where it's like, hey, this is my stack. I'm good at this stack. And it's not like your job's going to disappear. As a technology ages and becomes less of the leading edge project, its rate of change is probably going to decline, but its utilization doesn't. It may not get a lot of new projects, but the existing projects persist and they need to be cared for. And you are going to have folks that are jumping off. So the pool of developers gets smaller. The demand is still there. And so wages go up. The trick is to be aware of the state of the industry at the same time and make sure that stack you're working in, how you solve certain problems, right? I've even done a show on how you make web forms work on a smartphone. Doesn't make it a good idea, but the point is there that as the clients change, as the hardware evolves and that hardware is going to be introduced to the software you're maintaining, do you have an answer? Do you know what that looks like? And you can keep being a better and better expert in a particular stack. Or take the ride, jump on the new piece, learn again. Try something new. Try and find a COBOL developer right now who's able to retire. Because they don't turn those machines off. And they're not making many more COBOL developers these days. And so I'm talking to people in their late 60s, even in their 70s, making more money than they ever had before. And kind of like, I don't know how, I want to retire, but this is really a lot of money. And they're still depending on my code. It's an interesting trap, really, but it's one of the things that can happen with your career is you can choose to go in that particular direction and say, I'm going to be the specialist in this thing. I found a good place to work. They are going to keep running this software, and I'm going to keep taking care of it for me. Or you ride the new bits. Let's talk about artificial intelligence. And I use this picture for a very good reason. The term artificial intelligence is extremely old. It comes from the 1950s. But the first time that most people in the world heard it was in the movie 2001: A Space Odyssey, when it was Hal, who then turned around and tried to kill everybody. So, gee, I wonder why we have a weird relationship with artificial intelligence. I like this particular breakdown of all the different AI umbrella technologies. One of the things you'll notice right away is that AI is a description for technology that does not work. When it does work, it gets a new name. And the lines here are kind of clever. See the shortest line here with the planning, I'll use the clever pointer here. Planning, scheduling, optimization. So that's the technology that was developed in the 1950s, Marvin Minsky and his folks, the first time they used artificial intelligence. And it actually was part of the scheduling and optimization systems for the US military, right? That whole, an army travels on its stomach thing, that's software written in the 50s that makes it all work. And then there was an AI winter because it wasn't, sentient computers, so they happily bought that part and moved on. And in the 1970s, we got this new generation of robotics and expert systems. These were the Lisp computers. They sold several thousand of them. They were supposed to be expert systems. They hit their limits, another AI winter. And then in the 80s and 90s, we had the first generation of speech systems. Those are the ones you had to train, like Dragon Naturally Speaking things. They were kind of machine learning model, but you had to keep repeating phrases and so forth to help educate them, to get them to actually work. And then in 2011, 2012, with the adversarial neural nets, we've got things like Siri. And suddenly you didn't have to train them anymore. They just worked, unless you're Australian. And these latest generations of machine learning technologies now, things like deep learning, predictive analytics, and vision systems represent the latest incarnation of it. And if you talk, some of the scientists out there in this space are now saying we're headed into a new AI winter, and the rest of us are just going to work. Because you can add these vision systems to your software, right? If there's a reason to have an image recognition system inside your app, you can do this. My favorite recognition system, because it actually worked perfectly, right? And just this, just remind ourselves that vision systems have their limits. So yeah, sometimes we need vision recognition. Anybody played with chatbots? It's hard to call them artificial intelligence. It's more like artificial dumbness. But again, when we're talking about automation these days, the fact that we can build up semantic nets of information to answer questions and automatically, in some ways, build out a tier 1 customer support with it if you work hard at it. I also like bots in the Slack channels or in the Teams chats for passing along information, right, for doing builds. We used to do this with IRC back in the day. I would argue the most interesting technology just coming down the pipe recently is this form recognizer resource system that Azure, they're building inside of Azure. And on the surface, you're like, okay, cool, paper forms, scan them, but it actually break them down and pre-populate data and so forth. But I took that immediately several steps further. It's like, if you can recognize a form on paper, can you recognize my forms in my app? Because if I wanted to, why couldn't I use the recognizer to rewrite a web forms app in Power Platform? It's kind of the same thing, right? Just show me all the versions of the dialogue, snap them all, use the recognizer to break it down, show the data chain, generate the app for me. I talked to companies, they've got several thousand custom apps inside of their organization, and they're old, and the people who maintain them are gone, or behind a to-do list so long that no one can get to the bottom of it. Modernizing those apps is kind of an impossible task. How much of that could be automatable? You see machine learning models and being able to recognize forms. Forms over data suddenly becomes an automatable process. So some of this stuff was literally announced this week at Ignite. And it seems obvious to me that that's just a normal progression, that these will just be another set of tools for us as developers to pull together existing systems, take existing workflows, and turn them into new kinds of automation. If you're into data, predictive analytics has been around for decades, maybe longer. This idea of, okay, well, I sold this much last month, how much am I going to sell this month? And we've had lots of mathematical models for trying to do those predictions. The big thing that's happened in the past few years, and it continues to go on, is that we now have cloud and tremendous amounts of compute for this. So when I was playing around with data analytics in the 90s, that was a year's worth of planning to figure out different machine learning models to build a data warehouse on millions of dollars worth of equipment to try and guess get the kind of answers that people wanted then. It was very hard to be responsive to evolving business. Now I have cloud, and instead of having to figure out which one of these different cool analytical approaches I want to do, you just do them all. You got enough compute, knock yourself out. And I kind of don't have to build a warehouse anymore. I just store all the data I've got in a big pile, and I sort it out on demand each time, just throw more compute at it. And so these analytical approaches have gotten easier and faster and allow us to work on a larger diversity of data. And so we're taking steps beyond predictive analytics. You start putting machine learning models into this, and you get better predictions. You get unexpected predictions. They're able to test so many variations and look at trends, pull them out for you. And so these days now you're starting to talk to folks about prescriptive analytics, and you have experienced prescriptive analytics. So prescriptive analytics goes that extra couple of steps and says, not only what's going to happen next, but now let's consider all the possibilities of what could happen next and then prescribe the one that's most likely to be beneficial. So think about things like tickle emails. Have you noticed these days, if you throw a bunch of stuff in a shopping cart and close the page, a little while later you get an email from the site going, hey, you left some stuff in the cart. Would you like a 10% off coupon? There's some prescriptive analytics. No person looked at that, right? That's a little prescriptive analytics looking and saying, what's the most likely thing to get you to buy? Now, there's a little bit less sort of gross marketing things you could do here. I've seen prescriptive analytics systems used to figure out when to evacuate neighborhoods for forest fires. Because we know when evacuations kill, right? It's that kind of fright, older people, like you're gonna cost some lives or cause some injuries to evacuate. So do you evacuate earlier when it's under lower stress and maybe they're just vaguely annoyed by it, or do you wait till later when it has to do more stress? And there's software now. These predictive models can do prescriptive determinations to say, here's the chance for the fewest people to be harmed. Right? We see the same with maintenance of equipment. Steam turbines for power do need maintenance. The question is, when do you do it? How close do you get to it failing? Is it better to replace parts earlier when the demand is lower, or wait till failure and swap over and hope you can get it done before the next one fails? There's software tackling all of these problems. This is modern data analytics, and it's an interesting space, and it's only growing. We're only getting more sophisticated with it. And you can write video games. So the OpenAI Codex, where you can describe a game and it will spit out code to make you a really bad version of Asteroids. This is GPT-3, and of course it's not the coolest thing going on with GPT-3, not even close. Copilot's probably more interesting than that. I imagine some of us have played with this, where you're writing comments on code, and it's writing code for you. We just did a show with Michelle Manners, who's just out there, that recently published, and we were talking about, is this taking our job? And it's like, not really. You're still thinking of what needs to be built. What you're doing is spending less time wrestling with syntax, right? That's what this tool seems to be good at. You should be able to read the code it spits out, because no different than cut and pasting from Stack Overflow. Like, you kind of want to be sure of what's going on with that. So it's an interesting tool, and it does speak to a future where more and more our tools are going to help guide us to write better quality code. Conversations I've had on the show with guys like Mads Torgensen, where we're talking about, hey, .NET's 20 years old. How do I stop writing C# like it's 2005? Because all those commands still work. And we talked about tooling, that we could have tooling that's hinting. It's like, hey, I get that this is what you want to do with a string. Look, can I do a refactoring for you to use some of the features in C# 13? And make your code a bit faster, like all those kinds of optimizations and so forth. We could have more machine learning models around all of that. Our tools are just going to keep getting cleverer. They're just going to help guide us. So we spend less time wrestling with the syntax and more time solving our customers' problems. All right, let's have some more fun, more speculation, different code we're going to get to write. What replaces the smartphone? The smartphone has clearly won. It is the largest, most common computing device in the world. There are roughly 4 billion of them in operation around the world, more or less one for every adult human. We mostly, torment ourselves with these things, but in more developing parts of the world, this is the difference between life and death, right? This is the thing that actually lets you know when to plant, right? It's your smart almanac. Lets you know how to react in natural disasters. Helps you with resupply and water and so forth. These things have been pretty critical in Ukraine. Like, we're all cyborgs, right? We have a digital extension to ourselves now. It's actually part of your body, right? You see how upset you get when you lose it? And, the only reason we don't really consider ourselves cyborgs is because it's on the outside. I guess you could put it on the inside, but A, gross, and B, slows down upgrades, and that's not good. But this phone's been the same since 2007, more or less. It's been a slab of black gas. It gets bigger, it's smaller, taller, shorter, fatter. Sometimes it folds, sometimes it doesn't. 1 camera, 2 cameras, 3 cameras. I saw one with 5 cameras. I don't need that many cameras, but okay. The logical thing, of course, is augmented reality. This is a mock-up of what we think Apple's going to make. It's probably not even close. It's fake. It's a lie. Don't look at it too long. Here's a real one. This is the Qualcomm XR1. So again, a pair of goggles with some sensors on the front, tethered to an Android phone. Probably a bit more practical, reduce the weight on the face. Phone's in the back pocket. You've got a wire going to it. You can buy these today. They're about $1,000. If you want something that looks more like Google Glass, this is the Toshiba unit. It's the DynaEdge. Again, the future is here. It's just not evenly distributed, right? So we've got these devices out there, and we're starting to experiment them with certain environments. And of course, I'd be remiss if I didn't talk a little bit about HoloLens. All augmented reality devices, different from virtual reality devices. So something you look through that's also looking out at what you're looking at and adding information to you. So typical application, and these are real applications today, are in the industrial area. So when you're working on very expensive machinery that you have to do things correctly and safely, the fact that these glasses and their ability to see what you're doing create a detailed document of the process. They can actually give you the checklist in place so you're not looking down at other documents. They're actually marking as you finish each step before they present the next one. And they give you an ability to request an expert while you're working on something to be able to see through your glasses and add information, help you do more. I look at these devices right now because they're stunningly complicated machines, right? The HoloLens 2 is a complete computer battery pack on your head. It's pretty well balanced. It's also $3,500 US. And so it's not a consumer device. It's an industrial device. And as an industrial device, that means it also runs about $1,000 a month in IoT costs. When we've got the field projects out there now, it costs a lot to operate these things. Anybody remember the BlackBerry? The phone with the keyboard on it? Now, you probably remember the later versions, but the original versions in the 1990s, the only way you could make that thing work is if you ran a custom Exchange server installation in your company. You had to load on the BlackBerry enterprise servers and so forth. So you need a couple of guys in white lab coats just to keep that stuff alive. And then these phones were like $1,000 a piece, but you had email on your phone. Let me say that again, email on your phone in like 1998. Okay, now 10 years later, that wouldn't be a big deal, but at the time it was huge. That's exactly what these devices feel like right now. They are expensive, they need a lot of infrastructure to operate on, and so only certain companies are making it make sense. So if you're maintaining a $50 million steam turbine, a $5,000 headset that costs $1,000 a month to operate, not a big deal. But you're probably not going to play Candy Crush on it. What does the consumer version of this look like? Don't know yet. But it can do everything the phone can do and more, right? It opens the door to a different level of communication and access. The whole camera on your face thing, we'll get over that. Even if they look vaguely ridiculous, we'll get over that too, because this is also vaguely ridiculous. It's just this became socially acceptable once the device was good enough, right? Once upon a time, when you were carrying a smartphone around in 2001, you were pretty dorky. When the iPhone came along, it was so good that when somebody else said, hey, can I try that, you couldn't get it back from them. So I own a Google Glass. When I wore it out in public, and I really did, the normal thing people said was, can I try it? Then when they found it not compelling, they made fun of it. Okay? Once the device is compelling enough, the social contract will change. So let's talk about Meta. Oh, Meta. How do you turn a multi-billion-dollar organization into a smaller multi-billion-dollar organization? So let's face it, Facebook was up against it, right? With Apple locking down on advertising and so forth, Facebook's business model was already being disrupted. You can't blame the Zuck for trying to pivot. He also does own Oculus. And so he had the VR headsets. He's got to do something, so he goes all in on Meta. The problem is, it's Facebook. And you can't start with social media. You actually have to do something useful first, right? I don't even think he knows why Facebook was ultimately successful. But we've forgotten how much Facebook changed over the years from the early aughts. You know, for a while there, it was a college thing. Then you remember there was like the gaming wave. It was all about playing games on it, and then it became your community bulletin board. Now it's just like a bad TikTok impersonator. But we got these headsets, and literally this week, they announced the Pro. So the Quest 2, easily the best VR headset, especially for only about $400 US, is a really decent price. Now they've just put out this Pro. It's $1,500, so I don't know who the heck's gonna buy it. The main change they did was they balanced it better. So instead of just being a pair of goggles and straps, the battery's on the back, so it sits more comfortable in your head, but it is also heavier than the Quest 2. But inside of it are sensors for your face. So you now have facial expressions because it's looking at the expressions you make inside your glasses. Because what you really want to do is feed Facebook your facial expression data. Now, Microsoft just announced teaming up with them to do the Microsoft Teams in VR implementation against this gear. My thinking is they know that what Meta's building isn't going very well. Horizon World is so bad that not even the people that work on Horizon World are spending time in Horizon World. But there's also the Horizon Workplace, and that's that VR workplace idea, and now they're gonna work with Microsoft so that Microsoft has access to this hardware. So we could be doing Teams meetings in VR. I don't know that it makes me happy. Now it's just screens really, really close to my eyes, but it is an advancement. And these AR systems and VR systems are all programmed largely the same way. If you like C#, learn Unity. You can program a Quest with that, and a HoloLens for that matter. Or the Unreal Engine if you like working a little more low level. And there's other native solutions as well. But for us in our world, Unity's a good solution to that, and it's not just for making games. It's going to be about the VR space. I think what the metaverse needs is real work. I presume collaboration may be enough, but I'm still thinking about like reporting visualizations. Those hard analytics, you know, when you get to a point where your screen's just not big enough for the analysis you're doing, like, is there a three-dimensional way to do that that would be a better way to pursue an intuition about data? I don't know. It's the best idea I have so far. But that's what's actually going to establish this product, is in the enterprise, that kind of money, it makes sense if it gives a competitive advantage. I just don't think that the Monday morning stand-up in VR with facial expressions, so it's like, wow, I like the new headsets, now everybody looks sleepy. One last bit, and that is quantum computing by request. So quantum computing has actually made real progress. It's not just fictional, it's not far from done. This is a very challenging problem. In order to have reliable quantum states, you have to build a computer that essentially is submerged in liquid helium. Liquid helium is not fun to work with. It's so cold that you actually have to pre-cool the parts with liquid nitrogen first before you pump the liquid helium in, or you have a helium explosion. And in fact, if you want to have a quantum computer, one of the things you have to build into the structure is a venting system for a helium. And so if you lose control of the helium and it starts to overheat, you have to be able to vent it out of the building safely. It's not a trivial thing to operate a quantum computer. Over the past few years, we've had a few interesting steps in quantum computers. This is a picture of the Google Sycamore, which is Google's best effort. In 2019, they had a 54-qubit version of the Sycamore that did a test with 53 qubits, because apparently one of them was broken, using this thing called superconducting transmon qubit entanglement. And they ran on a problem that for about 200 seconds that was a random generator problem. And this is where they showed what they called quantum computing advantage. They said this would take 10,000 years in a conventional computer. Their rivals, IBM, then produced a result that produced the same result in 2.5 days with a conventional computer. But that's still 2.5 days versus 200 seconds. Although the Tawei Light supercomputer in China then ran a solution that took 300 seconds. So there's an interesting aspect of this whole quantum competition is you got a few different companies trying to build better and better quantum computers and publishing the results, and you also have the classic computers people trying to redo those same models, and it's forcing them all to get better. It reminds me of when, like, Internet Explorer and Chrome and Firefox were all dueling for better JavaScript rendering engines, and it made us all better. Quantum seems to be in that particular state right now. There's a bunch of different companies trying to get better. In China, the Zhejiang photonic quantum computer, about 113 qubits, did a 200-second run of a boson sampling model using quantum computation. Figure this would be about 2.5 billion years of classical computing. Nobody's really challenged that. I really appreciate this particular run because totally different quantum computer design, not even remotely similar. Photonic quantum is complex. And over on the IBM land, with their transmon architecture using a thing called, get this, transmission line shunted plasma oscillation qubits, they have a 127 qubit processor that started running last year. The test results have not been published. I was searching for them again today, so I suspect it didn't go well. Because generally, if the results are good, then you publish them, and then they get challenged, and you go around. So IBM had this roadmap with this 128 qubit processor called the Eagle that was going to be followed up this year with the Osprey with 433 qubits, no sign of it. And then next year, 1,000 qubits in a processor called Condor. So I think they're kind of up against the wall, having some challenges, but that's to be expected. You're doing original research. And I'd be remiss if I didn't mention UNSW here in Sydney. They've had a bunch of major quantum breakthroughs here. They're not making processors, but they are dealing with some of the problems in quantum computing. So dealing with qubit stability, stabilization, entanglement solutions, coherency solutions, pretty cool stuff. And I think it's great to see this cooperation going on. The real question is, what the heck do you do with quantum computers? Like, well, how would you do anything useful for them? Like, what's the problem? You're not going to play Candy Crush on them. So what are they for? And typically, the most common problems, like you usually hear about, in the news, you'll hear about, oh, they're going to destroy encryption, right? Which is not a very interesting statement. Yes, eventually, when we have million qubit quantum computers, we'll be able to decrypt 4096 RSA very easily. And there is a conversation going on right now that's saying, hey, if bad actors are siphoning up your encrypted data, they could be grabbing all of that so that they can decrypt it later when these machines come available, however long that may take. But that's not saving the world. It's not making a huge difference. The interesting space for quantum computers is actually quantum chemistry. So if we think about agriculture, we learned thousands of years ago to rotate crops. So you grew wheat on a given piece of land, and the next season you tried to grow it again, it didn't grow as well. You depleted the soil of some resources, and so you'd switch the crop. Instead of planting wheat, then you then plant beans. The beans actually would put stuff back into the soil. You'd pick the beans, plow the plants under, then leave it fallow for a year, and then you could plant wheat again. It would keep going. Crop rotation. We don't do that anymore because somewhere around World War II, we came up with the Haber-Bosch process. And the Haber-Bosch process was a way to make ammonia at scale. Now, they developed that during World War I because they needed to make bombs. Turns out it's the same stuff. It makes fertilizer, it makes bombs too. So there you go for the military. But the reality is this helped spark the Green Revolution. After World War I, with artificial fertilizers and modern planting techniques and new seeds, we were able to grow the world population from barely over 1 billion to 3 billion in a matter of 3 or 4 decades. It's an astonishing achievement, for better or worse. We've only doubled since then. And it's because we're able to feed everybody by doing this, making lots of fertilizer. It has consequences. It's also 1% of all our power consumption is making fertilizers and distributing them onto plants. And yet, the bean plant does the same thing. There's a rhizome on the roots of the bean plant that has inside of it an enzyme called nitrogenase. And nitrogenase is able to affix nitrogen and hydrogen together to make ammonia in the root of a bean plant. You know, not a lot of turbines and high pressure energy going on in there. Now, we've studied this particular enzyme for more than 100 years, and we know that there are iron atoms and molybdenum atoms involved in a catalytic reaction that puts the nitrogen and hydrogen together to make ammonia. We just don't know how it works. And the computational model to try and figure that out is too complicated for classical computers. There's too many electrons involved. It's a 2 to the 170th complex problem. This should be solvable by something along the lines of a 500 qubit quantum computer, depending on the particular style, in a few minutes. Now, what would that mean if we solve that problem? We now know what the catalytic reaction is that makes that nitrogenase enzyme work. So could we then recreate it in the lab? Instead of doing it plant, we do it with a device of some kind, a chemical reaction, so that we now have a low energy way to make fertilizers. So I immediately go to the idea of, at an individual plant, you have a little stake stuck in the ground that runs on a watch battery. It gets its nitrogen from the air, the hydrogen from water, and it just puts as much fertilizer as that plant needs at the time. So we reduce the energy impact of doing fertilization and get more precise with it. That's one. Battery technology is essentially alchemy. What we've gotten really good at is mixing different compounds together and then testing rapidly to see if we can make a better battery. And we have gotten better, but we don't really actually understand how batteries work. It's too complex to have an electron exchange problem. That's a quantum computing problem. Superconductors. We have a new generation of superconductors really developed in the 1980s, the rare earth barium cupric oxide superconductors. We know it's a phase state of matter, but we really don't know why it works. It's too complex of an electron compute problem. That's another one. There's about 300 of these. That each one, if we understood them well enough using a quantum computer, we could make a difference in make a better battery, make a better superconductor, one that could run at room temperature, doesn't need to be cooled by anything. All sorts of solutions like this. Better fabrics, better medicines, all from being able to do this sophisticated kind of compute. But they're all also deterministic problems. Like once you've solved it, you kind of need to solve it again. I'm really busy chasing around what's the quantum computing problem that's non-deterministic we'd have to do over and over and over that we need to keep going. Because maybe we only need a handful of these quantum computers, right? And that's an old quote from IBM, from Thomas Watson. It's actually apocryphal. He didn't really say it this way, but he said, maybe there's only a market for 5 computers. Of course, at the time when he was saying that, the computer looked like this, right? And it's hard to think, when you need rooms dedicated to the machine, how many of these do you really need? And I kind of feel that way about quantum computers. I've already described how complicated they are and how fragile they are. How many are you really going to need, especially if you're only working on a deterministic problem? It's very hard to look at this and see this. It's tough, right? It's hard to predict that. We don't know what a reliable large-scale quantum computer could do for us beyond this first set of problems. But we've seen that before. And that leads me to a story about William Shockley. William Shockley was one of 3 men who developed the original germanium transistor. This is a picture of that original transistor. And Shockley went on to create the Silicon Valley. He created a company called Shockley Semiconductors. And in Palo Alto, because that's where his mother lived. And the beginning of the Silicon Valley. And Fairchild Semiconductor, he went from these original simple transistors to substrate-based semiconductors. Now, he was struggling to actually understand all of the chemistry problems, and so he needed a computer. Now, this is before the silicon computer existed, before the CPU had been made. But there were computers back then. They just, looked like this. They were mechanical computers. Their bits were stored in ferrous cores or in vacuum tubes or in relays. They were computers. They were a long way from that silicon substrate that would build these really dense little computers. And yet, he used those primitive computers to model how the silicon substrate would work. And it worked. And he built some of the first semiconductors ever made and led to everything that's happened here. And maybe that's what's going to happen with quantum computers. That these unreliable, fragile, complicated quantum computers will be the devices we need to build a reliable, simple qubit that allows us to use them in many different ways. I don't know what that looks like. That's too far in the future for me. But I do know this. It's up to us to decide what any of that looks like. What's next is what we do. We make the future. And we can choose what the future we want. All of us in this room, we have those skills in different forms. There's just stories to be told and work to be done. Thanks for your time.